Okay, afternoon everyone, and welcome to the Elastic Load Balancing Deep Dive and Best Practices session. My name's Dave Brown. I lead the Elastic Load Balancing team, as well as a few other teams within AWS. I've been at Amazon for a little over 9 years. Started out on the EC2 team, and then sort of stayed within that organization for the 9 years, and have been running Elastic Load Balancing for about the last 3 years. So we've had a lot happening on Elastic Load Balancing this year, a few changes. We launched a new load balancer. So hopefully as we go through the session today, you'll learn a little bit more about Elastic Load Balancing in general, but also Application Load Balancer, which is the new load balancer we launched. So let's dive in. So what is Elastic Load Balancing? So Elastic Load Balancing automatically distributes incoming application traffic across multiple applications, microservices, and containers hosted on Amazon EC2 instances. So prior to August, we did not support the microservices and app and container use case. So we were instance-based. We've added that, and we'll talk a little bit more about that later. The next slide looks at a few of the sort of advantages of using ELB. So the first thing is the word we really like in the cloud is we're elastic. And what that means is you create a new load balancer, and that load balancer will scale to meet your incoming traffic. If you run a load balancer yourself, you've got to worry about scaling that load balancer, making sure it's highly available. You've got to care and feed it. With the ELB, you create the load balancer, register your backend instances, and the load balancer will scale dynamically. And secondly, and super important, is we're secure. So we pay a lot of attention to the security of the load balancer, but also features that allow our customers to be highly secure. Features such as managed SSL, and what are the very best ciphers and protocols to use on your ELB. We also integrated, and what that means is we integrate with up to 14 different AWS services. So whether it's CloudWatch for the ELB metrics, or it's auto scaling for dynamically scaling your backend fleet. We integrate Route 53 for DNS. We've very integrated CloudFormation, number of services that are integrated with ELB. And then finally, we're cost effective. So the cost of ELB is significantly cheaper than actually running the load balancer yourself. So if you had to run a load balancer on EC2, it would almost certainly cost you more than actually using an ELB. So it is quite a good deal. So as we think about building an application, I'm sure many of you have had an architecture that looks like that. Not one I'm recommending. It's not a best practice, but it's where a lot of us start, right? We build an application on a single instance. You maybe even put your database on that instance. Everything's on that one machine, and you're showing how this application works. Well, not something that's recommended. Obviously, there are a couple of challenges there. One, that machine could fail. If that machine dies, obviously the web server goes down or whatever you have. Secondly, if your traffic spikes, well, that machine's not going to handle a certain amount of traffic. The other thing that we kind of take for granted, and I was a software engineer back in the day at Amazon as well, and we don't realize just how good load balancers make us look as software engineers. And we have things like garbage collection in Java, where your VM stalls. You may have memory issues. Some of you guys that write C, and you want to just basically do an assert and bail out of the application if anything happens. The load balancer just papers over all of that. Anytime something like that happens, the traffic just magically goes elsewhere. So here's a solution that I would recommend, or an architecture that looks a little better, right? So yeah, we have an elastic load balancer taking traffic and spreading that traffic over 3 instances. Any of those instances fail, load balancer will automatically detect and shift that traffic onto the remaining instances. With auto scaling, you can automatically scale that backend fleet, and the load balancer is going to scale dynamically as well if the traffic increases. So it takes care of a lot of those challenges we just spoke about. It's highly available. I wanted to go into a couple of details. We don't normally talk about internal architectures of AWS services, but this is one where I think it's important to understand. So every single elastic load balancer utilizes multiple availability zones, even if you as an application developer isn't doing that for your application. Obviously, it's highly recommended, but something that we do. So here's the architecture. So essentially, on the right-hand side there, you can see we have the customer's VPC. That would be you and your VPC. And on the left-hand side, we have the ELB VPC. So we actually run in a VPC just like you do on EC2. So we're also a demanding customer of the EC2 team. We then have some subnets in each availability zone, and as you can see there, we have an ELB in the subnet on the top and an ELB in the subnet on the bottom as well, forwarding that traffic into your subnet. So we're pretty much running alongside you. We have the ability to get that traffic securely injected into your VPC. One thing I wanted to cover, and this has become more important with the recent launch of application load balancer, is we're starting to explain to customers really what are the different types of load balancing. There are really two different types of load balancing. The first one, which we talk about, is network, or you'll hear TCP load balancing, or if you really understand the networking layers, you'll talk about layer 4. What this does is this is really basically connection-based load balancing. So requests are flowing through the load balancer, but we're not looking at any of those requests. We're just handling those packets and forwarding them to the backends. And that supports things like TCP and SSL. Client connections are bound to a server connection, so every single time a new request comes in, it's actually bound to a backend instance that will never move. There's no header modification, so we pretty much can't do anything with that request. We just pass those packets through. If you want to know about the source IP of the client that's connecting to you, there's no X-forwarded 4 header, nothing like that, because we can't actually do anything with the request. So there's a feature called proxy protocol, which comes from HA proxy world, which allows you to forward the source IP through to the destination. So that's layer 4. On the other side, we've got layer 7. And many of you might be more familiar with these or prefer these features, and that's what we call an application load balancer, or HTTP and HTTPS. Now, this is where every request that's coming in, we're waiting for all the packets to arrive, we're reassembling the HTTP request, we're looking at the headers, we're doing a lot of work in the load balancer. And the connections are actually terminated at the load balancer, and then we have connection pools to your backend instances. So you'll see us open up multiple connections to your backends, and we'll use those connections to forward the requests. And obviously, headers may be modified, like we may insert an X-forwarded 4 header with the source IP of the original requester. So for many years, since 2009, ELB has supported both on a single load balancer. So we've had what we call now the classic load balancer. Previously, it didn't have a name. It didn't need a name. It was just ELB. Now it's the classic load balancer. It supported both layer 4 and layer 7. But the layer 7 support has been, it's been okay. There's some decent features in there, but it's not the depth of layer 7 support that many of our customers have been looking for. And really what you see in there is very much Amazon's approach to load balancing. Amazon internally, we actually treat load balancers very simply. We just basically, as long as you give me a VIP, an IP I can talk to, backend instances, a health check, and the ability to send traffic, we're good to go. Anything else, we're going to probably put into our application stack. But many of our customers are really looking for a richer layer 7 experience. Hopefully many of you. So in August, we announced the application load balancer. I chatted to a few customers who said they only heard about this at reInvent this week. So it's been announced since August and been available, and customers have been using it. We've been seeing great adoption. So to give you some idea of the features, so if we look at Classic, it supports TCP and HTTP, whereas application, because it's only application, it's layer 7, it's only supporting HTTP and HTTPS. From a platform point of view, so now we're looking at the EC2 network architectures. The Classic supports both EC2 Classic, that's not confusing at all, as well as EC2 VPC. So while the application load balancer supports VPC only. So if you have any applications that are still running on the Classic network, thank you for being on AWS for such a long time, and let us know if we can help you with the migration. From a health check point of view, Classic supported health checks, but the application load balancer has some nice improvements, which we'll talk about a little bit later. CloudWatch metrics, obviously they both support those, although we took a long look at our CloudWatch metrics, and I think we've improved them quite nicely. And then some things that the application load balancer supports that are new. So the first one is in the world of content-based routing, and so we allow path-based routing. So this means I receive a request, and that request I can actually look at the packets and forward it to a different backend based on the path of the request. And then obviously container and microservice support. That's massive given our customers are moving to containers. And then native WebSocket and HTTP2 support. So we're catching up with all the modern internet applications. So let's take a deep dive into that, application load balancers. So the first thing to say is we didn't just change classic load balancer. We've built an entirely new load balancing platform, right? Pretty much a large part of it is brand new. So because of that, we wanted to be very transparent with our customers. We didn't want to go and change things behind the scenes. The classic load balancer interprets HTTP in some slightly different ways at times to the way that the application load balancer does. So we want to say, hey, fully transparent with our customers. It's a new load balancer. If you move to this, test it. See how it works for your application. Let us know if there are any challenges. What we've seen so far, almost all of our customers have come back and said it's amazing, working really, really well for us in our applications. It's obviously fully managed, scalable, and highly available, just like the classic load balancer was. And then it supports the content-based routing feature. Super important feature, as I said earlier. So The really big benefit of that is that a single application load balancer can actually host multiple applications. Whereas previously, if we look at the classic load balancer again, your single ELB could host a single application, right? And if you did want to host multiple applications, well, the way to solve that, and the solution was, well, just use DNS. So in this example, we have an application handling our orders, and we have an application handling images for our website. And what I do is I just use DNS. So from my client or from my web browser, when I want to go to orders, I do orders.example.com, and that'll route up to the load balancer at the top. And when I want the other one, I do images, and it routes via DNS to the load balancer at the bottom. That works fine. But you are paying for 2 load balancers, and you're having to manage 2 load balancers, and that, it could be better. So what application load balancer lets you do is, well, let's just have one DNS name. Let's just have example.com. And now in the path, I've got the word orders or images. So using path-based routing, which I can set up as a routing rule, the condition is going to say, if anything in the path matches orders, and you can use wildcards here as well, basic glob functionality, forward that to the target group. So that blue box is called a target group. Forward that to the target group for orders. And if anything has the images, forward that to the images application at the bottom. And today you can have up to 10 rules in your application load balancer. So you could host up to 10 different applications behind a single load balancer. Great. Big benefit. So it's a significant cost saving. If you're running multiple load balancers just because you have single applications, you can go down to a single load balancer, use path-based routing today, and have one application, one load balancer. So you can just decrease your hourly cost. Obviously, your bandwidth cost will be roughly the same, assuming you're sending the same amount of traffic. One thing we see customers say is, that's fantastic. I've currently got hundreds of load balancers. I'm just going to go down to one load balancer. So what you do want to think about is you think about your architecture. You could do that, could be supported. But when we think about blast radius and isolation. So if it was me doing this for my teams, running application load balancer, I'd probably look at an application load balancer per service, or maybe per service team. We have the 2 pizza teams at Amazon. Something where the service teams operate on that load balancer, have full control, rather than one load balancer for the company. Just trying to risk the single point of failure or configuration nightmare that could turn into. So we have multiple applications behind a single load balancer, cost-saving improvements, management improvements. It's a big change. Next, we want to look at the ability to support microservice architectures and container-based architectures. So obviously, application load balancer can do that. Otherwise, it would have been an irrelevant slide. But the way we do it is multiple ports. So with classic load balancer, you had to register an instance with the API. And when you did that, you could only give us one port at a time for that instance, and then you were done for that instance. If you try to give us that instance again, we would tell you, nope, that instance is already registered. So it meant running containers on a single instance is incredibly challenging, because when you run a container architecture, regardless of what platform you're using, it's going to try and select dynamic ports. So you have no control over the port that it listens on. Not all your containers can listen on 80, because there's only one port 80 available on that box. So they're all going to choose a dynamic ephemeral port, essentially, and your load balancer needs to be able to use those. So with application load balancer, when you register an instance, you can give us a port, and that together is unique. So you can give us that instance again. As long as the port's different, you can keep registering. So you can register an instance as many times as you like, well, obviously 65,000 or so. And we will route requests on those ports. So it gives you the ability to carve up a single instance. If you use Amazon ECS, which is the EC2 container service, ECS will actually manage all of this for you. So you just tell ECS, here's my task, there's my load balancer, and it'll actually launch those containers and register them with the load balancer automatically. You don't have to think about it. So, but don't think that it's only supported with ECS. Even if you're not running containers, you're just running a few applications on a single instance, and they're listening on different ports, you can still register that instance multiple times with the same load balancer on different ports. So that's the big functionality there. So to give you some idea of how this works, I mean, in this slide we had EC2 instances as part of the target group. Again, the target group is the logical grouping of machines behind the load balancer, the dotted blue line. We can turn those into containers. So I just turn them into containers. So now you have ECS containers running there, and you can mix and match. As long as your target groups only contain like EC2 instances or containers, but you kind of run the same thing, keep your target groups homogeneous, but you can have target groups, some of them are EC2 instances, some of them are containers, as you move your application. So again, keeping on the cost-saving theme, with containers, one of the great things is you get better utilization of your EC2 hardware. So you can carve up a single EC2 instance now into much smaller chunks or slots and drive up the utilization of that machine, whereas previously with ELB, you may have had wasted capacity on those back-end instances because maybe a T2 micro was too big for your microservice, right? And you still had wasted capacity. Now you can really get all the capacity out of that. So that's containers. So let's look a bit at the API. This was very interesting for us because, I did a lot of work on the EC2 control plane. Maybe I shouldn't have told you that, but we really prioritize backwards compatibility, right? So many of you guys have done API work. What is the #1 rule in designing APIs? It's like, don't bake backwards compatibility. Like, find a way to make this thing work. And when we launched this feature, we broke backwards compatibility. And it took us about 9 months to get to a place where we felt good about it or okay with it. And the reason for it is we realized that the original ELB API was just too simple. We went at it with every single angle to try and put all this layer 7 functionality into it. We just couldn't make it happen. So eventually we said, you know what, customers want this functionality, and we can actually give them a better API that solves a couple of the challenges we've had on the old API, some of the design decisions we made that we wanted to change, and is future focused, so it can support all the layer 7 features we want to do going forward if we just broke backwards compatibility. And I'm happy to tell you that all the customers I've spoken to have been happy with that decision. So it's the one time in my career that I've broken backwards compatibility and I've gotten away with it. So I think it's been good. Obviously, the SDK integrates, there's CloudFormation integration, so it's very easy to do, but you'll see it is a new API. The console, if you use the console, it's exactly the same experience. You don't even know that it's using a different API behind the scenes. It's a newer API now, so it follows a lot of the best practices that AWS has learned over the years. The original ELB API was 2009, which was early days. And we've also got quite a few new resource types. So previously, we had a load balancer. It was very simple. You had a load balancer, you added instances to it. To support all the new functionality, we've added things like target groups, targets, and rules. So I'm going to walk you through what this the model of the API looks like so you can understand it a little bit better and think about how you would map your application to an application load balancer. So obviously, we still have a load balancer. We didn't get rid of that. And we still have listeners, which we had previously. So what is a listener? Well, a listener defines the port and the protocol on which the load balancer listens. It sounds pretty obvious now that I say it. So if you want a website listening on port 80, what you would do is you'd basically say, I want HTTP, or ideally HTTPS, on port 80, and that listener would then start listening and accepting incoming requests. You have to have at least one listener per load balancer, and you can have up to 10 listeners. Right? If you need more than that, obviously just like EC2 instance limits, you can always come and talk to us and we see if we raise it for you. Routing rules, the ability to route, this content-based routing, path-based routing, are defined on your listeners. Right? So we all got what listeners are. So let's go to the next. Now we're looking at target groups. So what I've shown you there is the dotted target groups, and you can see I've got 3 target groups in this architecture together with health checks. So logical grouping of targets behind a load balancer. So we've called them targets. We haven't called them EC2 instances. Right now, we support EC2 instances and containers, but they're targets, right? Target groups can exist independently from the load balancer, so you don't have to. You can have a target group defined and just add the resources to it, and at some point map it to a load balancer or map it to multiple load balancers. And the other really nice thing is targets are regional, but they can be associated with an auto-scaling group. So you can actually have an auto-scaling group scaling each one of those target groups individually. So because they're separate applications, they're going to scale differently, but you want your auto-scaling to scale them individually. So that's target groups. So let's build the picture up. And health checks are obviously defined on the target group. So now we're looking at the targets. So I added the EC2 instances there. So what is a target? So obviously a target's a logical load balancing target, and today it can be an EC2 instance, a microservice, or a container. And it can be registered with multiple ports. We spoke about that. And a single target can be registered with multiple target groups. So if you have an EC2 instance and you actually want it to exist in multiple applications or it's hosting across multiple applications, there's nothing stopping you from just taking that instance and registering it multiple times. You do need to be a little careful. This is a lot of rope we're giving you. You can come up with some very interesting architectures. I have seen some incredible architectures that customers have come up with using this. So you want to just keep thinking about availability and maintainability, but you can do some interesting stuff. So we got that. So how do we link these together? So no traffic's flowing yet, because I've got my load balancer, my listeners, my targets, but I haven't linked them together. So let's link them together. So obviously we link them together with something that we can't read, and that says rules. Right, so we're looking at the rules there. So in the middle, you've got the default rule, you've got an image rule, and I think you've got an orders rule. So we do support a default rule. A default rule means if this request doesn't match anything in the path or none of my other rules, just send this to that target group. So you can have a load balancer with just one default rule and one target group, and it'll work perfectly fine, very similar to what the classic load balancer does. But you can fall back to default as well or have more specific ones. So we look at rules. What do rules support today? So they provide a link between the listeners and the target groups, and they consist of conditions and actions. So every rule is a condition, and then what action do you want to follow? Today we have one action, which is the forward action, which will forward a request to a target group. So when a request arrives, we look at the condition, we run through all the rules. When we find one that matches, we forward it to that target group. If we don't find one that matches and you have a default, we will use the default. If there's no default, we will return a 503. And today you can do path-based rules, so you have to give us a path pattern. And you can use, paths are obviously case sensitive, can be up to 128 characters in length, and those are the various characters that can be included in your normal URL style path. So that was a whirlwind tour of what the architecture looks like, but you can kind of see how it all hangs together. It's all available in the console, very cleanly laid out. Yeah, APIs are nice and clean and new as well, so it should be pretty straightforward. So let's see if we can pull a rabbit out of a hat here. So today we have load balancers that support up to 10 rules. So we launched with that. We said, who could possibly need more than 10 rules? Well, it turns out most people actually need more than 10 rules. So we decided, okay, well, let's remove that limit. So in the very near future, you come talk to me, we can make it sooner. You can have, it says up to 100 rules, but it's like 100 as in you can have 20 EC2 instances on a new account. We can raise that up if you want. So we're sort of removing the limit from rules. So it'll be available publicly in the next few weeks, but we do have a beta available now. Oh, the other thing we added was deletion protection. Every now and then I get a frantic call from a customer. Dave, I just deleted my main load balancer. Can you help me? And some of the times we can. We go in and we see, oh, look, those IPs are still available, and we can kind of reconstruct the thing. We actually have an API internally that's just undelete the customer's load balancer now. So we decided rather than making my engineers do that all the time, it doesn't happen too often, we should probably give it to customers. So amazing feature. You can actually say, don't let me delete this load balancer via the API. And then if you try and delete it, it says, sorry, you can't delete it. And then you have to go and remove the deletion protection, and then you can delete it, right? So good feature to use. Application load balancer provides improved performance for internet applications, right? So we spoke about this a little bit earlier, but there are a few things in here. If you're running an application on the internet and you don't even have a need for path-based routing, it's a really good idea if it's HTTP to consider application load balancer. So some of the things there, so native support for WebSockets. Basically, WebSockets have been around for a year or two. Basically allow full duplex communication. So we have a lot of customers doing it for things like Twitter feeds and your sports feeds, where you've got an iPad and you want to connect to the load balancer, and from the server you want to be pushing content to the iPad or pushing to the device. So WebSockets are letting you doing. So previously customers would use TCP load balancing on Classic. Now you get full WebSocket support. HTTP 2 is obviously the newer version of the HTTP protocol. Significant improvements to page load time. So it can do sort of multiple pages load, multiple requests to the server at the same time. So we support HTTP 2 out of the box as well. And then improved performance for real-time and streaming applications as well. So classic load balancer, if you were doing very large downloads or you're trying to do streaming through the load balancer, there were some challenges there, and they used to do quite a bit of buffering, and that's not great when you're streaming. Application load balancer solves all of those problems. Important tip. So there's no additional configuration required to use WebSockets or HTTP 2. I've actually thought about adding a checkbox to the console that does nothing at all, just to say I want WebSockets and I want HTTP 2. Because the number of customers that have said, how do I turn on WebSockets and HTTP 2? It's on by default. It's just on the load balancer. It actually happens all in the request path. So WebSockets will be upgraded automatically to a WebSocket connection. You don't have to do anything. So we have another hat over here. Classic load balancers have offered IPv6 support for some time. Actually, that's since around June 2011. There's actually a day every year called IPv6 Day. International IPv6 Day, and we launched IPv6 support on classic load balancers back in 2011. We've also supported them on both classic and VPC. If you do want IPv6 on VPC, we can give it to you. But that kind of doesn't matter because in the coming weeks, native IPv6 support is available on all application load balancers. So obviously in VPC is only, and this is full IPv6. The other thing that's going to be available is IPv6 on EC2. So you get full IPv6 between EC2 instances, egress to the internet, everything. Okay? The world's been waiting for IPv6 for like 20 years now. So, okay. And then improvements to the application availability and scalability of the load balancer. So these have been, you know, if I look at where we spend our time on ELB since I've been on the team, like our number one priority, there's really three. We have three number one priorities: security, availability, and scalability. We just cannot drop the ball on any of those. I mean, you know, if you have a load balancer that does something strange, it's infuriating. And we just have to make sure that they are highly available and highly scalable all the time. So if we come back to, you know, that we all realized that this wasn't the architecture that we really wanted. You know, we don't want to be building applications like that. We want it to be super highly available. Let's look at a few things we've improved in application load balancer. So the first one I spoke about a little while ago is health checks. And they allow for traffic to be shifted from an impaired or failed instance. So this is a health check behind the load balancer. And the way this works is the instances are running along, they're all taking traffic. You suddenly have one instance that has some sort of problem, right? Like CPU starts to spike, maybe you had an infinite loop or you memory issue, whatever it might be. The health check will start to fail to that instance. So we stop sending traffic there. And that all happens within a few seconds. So, you know, often less than a second. So this health check runs every few seconds. As soon as you detect a failure, which you can define, so you define what URL we're going to call, we'll shift traffic away. When the instance becomes healthy again, we'll shift that traffic back again. With auto-scaling as well, you can set auto-scaling up so that if any instance fails a health check, it'll actually remove that instance out of service and replace it as well, so that even the mitigation of a failed instance can all be automated. So we look at what we support. So with application load balancer, obviously it's not TCP health checks, it's just HTTP and HTTPS. You can customize the frequency, the failure, and the one thing you can do that you haven't been able to do previously is the list of the actual return types, so successful response codes. So previously on classic load balancers, you had to send us a 200. If you didn't send us a 200, we considered it to be a failure. And lots of applications return like 301s for health checks and other things. Now you can say to us, hey, if I give you a response, just accept it, right? And then the one I like the most is detailed reasons for health checks are actually showed via the API in the AWS Management Console. And this was one of the largest number of dev support contacts for ELB was, why is my health check failing? So based on that feedback, we just thought maybe it's a good idea just to tell you in the API, in the console. So if your health check's failing, it'll now say, hey, we've seen a timeout, or we've seen a connection error, or you know, we're actually returning some code that doesn't match. So you'll actually see that in the console. It just saves us an enormous amount of time. I mean, it saves you an enormous amount of time. And then the other change here to keep in mind is with classic load balancer, if all your health checks fail, so if you fail all the health checks to your backends, we will return 503s. So we say all instances are unhealthy, let's return 503s. With application load balancer, we've taken a different approach. We say if all those machines fail, we're actually going to fail open. Because if everything's down, we may as well try and just send the traffic somewhere. It's very likely that the connection's going to fail and we send a 503 anyway. But if everything fails, we're going to fail open. And there's one of the great things with this approach is we do have from time to time customers that have configured their health checks that are too deep in the system, right? So you may have a customer, we've seen situations, customers have every health check hit their master database. And if it doesn't get a successful response from that master database, and by the way, there's only one of those master databases, but there might be 10 application servers, and that master database has some sort of hiccup, all those servers go out of service. And what would have been just a few seconds of impact on the master database, now all of a sudden you took all your servers out of service and your whole application is returning 503s. So this will actually protect you against that situation. But there's another point there, or best practice, is think about the depth of your health checks. Ideally for me, most health checks should really just check the health of the machine behind the load balancer. Like try and avoid like hitting a website out on the internet, which I've seen before as well. You just ideally keep it isolated and be careful of things that are regional as well. So you've got a regional resource that you're trying to include in your health check. My guidance is typically keep them as shallow as possible and think deeply about them because it is a risk. It's less of a risk in application load balancer because we do fail open, still not great. And I'm sure if you've been around any AWS employee for even 5 minutes, they'll give you this advice. Always use multiple availability zones. And we spoke a little bit about how ELB does that, where we always run in multiple availability zones. And what I want to show you here is even if you are only in one zone, we will actually route that traffic from another zone through to you. And our goal here is really to never have an elastic load balancer fail. So if we have any problem in a zone, we will always be able to serve the traffic out of the other zone. And that traffic will automatically shift from a failed zone using Route 53. So all that is actually automatically done via DNS. And then we often have customers, you say, well, I run in one zone because of cost. And cost is a serious concern. Sometimes we don't want to spend the cost for additional zones. So we actually, at Amazon, we typically always run in 3 zones. 2 zones where they're available. If there's 3 zones, we'll always choose 3 zones. And the reason being is, being in one zone is an availability risk. Because we say that's a unit of failure, isolation. If that fails, we could lose a zone. We guarantee you'll never lose 2 zones for the same reason at the same time. They don't want to really be in one zone. Well, let's go to 2 zones. So in this example, I say I need 6 machines to always have enough capacity. So if I go to 2 zones, well, now I've got to say if I lose a zone, I still want to have 6 machines. So 6 plus 6, I need 12 machines now in 2 zones to actually handle all of my requests, because I've got to be scaled enough to lose a zone. Well, what happens if we go to 3 zones? So if we go to 3 zones, well, now if I lose 1 zone, I'm still going to have 6 machines. And to do that, I need to have 3 machines in each zone. If you guys do the math on that, which I did before the talk to make sure it's correct, that's actually only 9 machines. So I only need 9 machines now, not the 12 machines. So actually running in 3 zones can often be cheaper than running in 2 zones to be scaled for your load. An application load balancer will support that. So one of the things we do see is there's sometimes multiple challenges, or at least one I'm going to talk about here, running in multiple zones. And one of those is your clients are resolving DNS to enter the zone. So sometimes you'll have DNS providers that cache DNS, or you'll have clients that just resolve DNS once and never do it again. Java is actually pretty bad at that, right? Unless you set the X header, Java will actually do that. Resolves it at startup and never does it again. And they're very sticky to one IP. But you get these sort of imbalances in traffic. And that can often cause, as you can see there, one of your zones to be running taking a lot more traffic than others. And the way we solve that is we actually just use a feature called cross-zone load balancing, which will actually send the traffic from the load balancer to multiple zones behind the scenes. And the great thing there is you just see all of your zones just get exactly the same amount of traffic. It's actually even better than that, because my clicker's not working here. So what it's actually doing is it's distributing that traffic so evenly that you get the same amount of traffic in each zone. And the other thing is, even if you have an imbalance in EC2 instances, even if you have 1 instance in one zone and 3 in another, the zone with 3 is going to get 3 times the amount of traffic, and the zone with 1 is going to get enough for that 1 instance. So it actually does it at a per target level. So you're going to get a much better case. All your targets are going to get the same amount of traffic. And then the really amazing thing is there's no additional bandwidth charge for the cross-zone traffic. So we actually removed the normal bandwidth charge for cross-zone out of this. So you can do this with ELB and not pay for that cross-zone traffic bandwidth charge. And cross-zone load balancing is actually enabled by default on all application load balancers. So on classic load balancers, it wasn't enabled by default, but on cross-zone, on application load balancer, we said it is. You actually currently cannot turn it off. It's not disable, but there are valid architectures where you actually do want to turn it off, and you want to be very, very zonal. So we are going to be adding the feature to allow you to actually disable cross-zone load balancing. And then auto scaling. One of the big changes I mentioned earlier is auto scaling will actually now scale at the target group level. So to give you some idea of how that works, so we've got 2 target groups here with EC2 instances in them, taking a certain amount of traffic. Traffic to the target group at the bottom increases. You use the CloudWatch metrics with auto scaling to tell it to start adding machines, and auto scaling will actually scale that up. So, I mean, it obviously makes sense given that you've got different applications hosted behind your load balancer. They're doing very different things. Your orders could get a lot less traffic than your images. You could see spikes on the different ones. You want to scale them independently. So if you use application load balancing, auto scaling can scale the applications independently, right? Different target groups. Then one of the things that actually took me a while to realize this as well is many of you have applications which have a daily peak, right? So where we have at Amazon, obviously retail, we have a fairly substantial daily peak every day, and we see that many of our customers have the daily peak in their traffic flow. When you're using auto scaling and you're actually following that line of trying to scale your machines to that, kind of remember you're at peak all the time. Because when you're at your lowest point, like mentally you're thinking, it's not a busy time for the service right now. We're at the low point, but you've taken away all the capacity. So we've sometimes seen customers actually at their lowest point every day run into 503s and surge queues and problems with the load balancer because they just haven't realized that I'm actually running kind of at peak all the time because it's utilizing just enough capacity all the time. So just something to think about with ELB and autoscaling is you can actually see problems at your lowest point if you're taking away too much capacity. And then our security features. So back in 2014, it was well-timed, given it was a couple of months before Heartbleed. Some of you may remember that event. We took a look at our SSL ciphers and protocols, and we said, customers, it's become so complicated. Like, every month I'm hearing about some new vulnerability, and what should I do? And it takes a lot of time to become an SSL expert. And if you ask a lot of the security experts, they'll often tell you, well, this is the set of ciphers and protocols you need to use. And when you actually go have a look, they're super secure. And the reason they're secure is no web browsers yet implemented support for those ciphers and protocols. So we had that internally in Amazon. We were given some advice similar to that once. So we said, well, as ELB, we need to staff up and we need to take control of this. We need to make sure all of our customers have got the very best ciphers and protocols, and we can't expect them to be experts in this. So we added, with SSL offloading, we added SSL negotiation ciphers. And the way we do this is I have a couple of engineers on my team that are very involved in the SSL community. Colm McCarthy gave a talk earlier about a version of pretty much an SSL or OpenSSL kind of library that we've written ourselves that's been open sourced. Great talk. I'm sure it'll be on YouTube if you missed it. But we said, so we've taken a look at all the ciphers and protocols, understand deeply all the vulnerabilities. The other thing we do is we run all of Amazon.com's traffic. That's one of the great things at Amazon. We just go grab that entire traffic stream and say, okay, let's run this through an ELB. And let's see what happens. It wasn't the live traffic. It was just to siphon some off. But we run all of that siphon that traffic off. And we then go and look, and we add this cipher, and we see, oh, boy, if we add that cipher, we see a 30% drop in clients being able to connect to us. We can obviously see the user agents as well, so we can see, oh, well, look, all the Windows XP machines just dropped off. We better put that one back. And so we do that, and that gives us the absolute best ciphers and protocols for your application, based on pretty much every user agent we can find out there. A couple other ways of doing that as well as the ability to connect. So the very best security best practices and the ability to connect from as wide a range of clients as possible. So if you're using Classic, we always recommend use the latest SSL policy. If you've defined your own policies on Classic, that's fine. Take a look at how they differ and maybe have a look at whether you should just migrate to the managed one. On application load balancer, all the policies are managed. So you'll always get one of our managed policies. We just think that's a better way to go, just given all the problems we've had in the last few years in this space. The other thing we added last year was ACM integration. And thanks, I actually completely forgot about this one, and somebody in the audience told me about this beforehand. Thank you. And I'm like, let me go add a slide quickly. So that was what I was doing up here. So this slide is hot off the press. But we have ACM integration. So ACM is Amazon Certificate Manager, and what gives you free certificates. So you basically go to Amazon Certificate Manager and give me an SSL certificate. They'll give you one. And you just then associate that with your ELB. Super easy to do. And the best part, you never have to think about it again. Because when that certificate comes up for renewal, Amazon Certificate Manager actually manages the renewal process. Now, I don't know about you, but I've never had an SSL certificate expire on me unexpectedly. And all of this, and it's free as well. So it's an amazing service. If you're not using that or you're coming up for renewal, absolutely think about using ACM. All right, we have another hat. That's pretty cool. So application load balancer currently today supports security groups. So you can control traffic to your load balancer with security groups, right? So you can specify CIDRs and say, I only want people from within my organization to connect. Some customers have said, hey, you know that feature on CloudFront called WAF, Website Application Firewall? It'd be pretty cool to have that on ELB. So we thought so as well. So we've added WAF to application load balancer. And that'll be available soon in the coming weeks. So with that, you'll basically be able to, well, I actually have a slide for that. So with a website application firewall, basically monitors and protects website application from malicious activities. So any request coming through gets inspected by WAF. You can configure rules to either allow or block or count. And you can do things like SQL injection, cross-site scripting, bad actor IPs, bad bots, HTTP flood attacks. And I know they're going to be adding more and more and more rules. So you can go into the WAF service and you can configure this. Once you've got all your rules, and they've got some great custom rules there or previously defined rules, you just associate that with the ELB, and we'll take care of that. So I think that's a pretty cool feature coming in the next few weeks. And then we look at monitoring. So we improved some of the load balancer monitoring as well. So obviously, we've worked out how to have a highly available application, how to host multiple applications. So we need to be able to monitor this thing. So CloudWatch metrics. CloudWatch metrics have been there on application, on ELB for some time. We added them some time. But on application load balancer, we've made some improvements. So they provide detailed insight into the load balancer traffic. They're all provided at the 1-minute granularity. So if you are using that feature in CloudWatch, you can get that. And metrics are provided with application load balancer. Metrics are provided at both the global application level, at the load balancer level, as well as at the target group level. So again, you want to be able to see metrics at the target group level because those are different applications. They're going to behave very differently. And you can configure CloudWatch alarms. You can also integrate with auto scaling. So any one of these metrics, you could integrate with auto scaling and say, if that metric spikes, scale up. If it goes down, scale down. So I just want to look at a couple of the metrics very briefly and give you an idea of, what are they, how do they behave, what do they for? So firstly, healthy host count. It's the count of the healthy instances behind your load balancer or behind the target group. And it's important to consume that at the zonal dimension. If you see this failing, normally when this fails, it's your health check is failing. The most common reason for a health check failure is a timeout. So those health checks give you 1 second to respond to us. If you don't respond in 1 second, we consider you to be failed. All right, so keep that in mind. Normally, it's a timeout. The other one is latency. So latency measures the time from the point that your packet leaves the load balancer into your application to when we first see the response. That's how we measure latency. So it doesn't include the load balancer time. And we provide min, max, and average of that. We also have access logs we'll talk about shortly. And then we have a rejection count as well. So important difference here. Application load balancer doesn't use surge queues. A surge queue is basically when a request comes in and your back-end applications are all super busy, we don't have anywhere to send it to, we will store it in the load balancer for a period of time. On classic load balancer, we'll store up to 1,000 requests per IP address in your load balancer. But one thing we've learned at Amazon over the years is surge queues are normally a bad idea. And the reason for them is you get clients out there calling you, their thread pools are stuck waiting on your load balancer. They're not doing any more work. They're waiting for a response. And by the time your 10-second or 10-minute or whatever the outage is over, you're now going to go back and process a couple of thousand requests that are 10 minutes old. And that client is long gone. So actually with surge queues, you can actually get to a situation where a failed load balancer can actually cause other services to fail as well. You just get everything gets stuck on this load balancer. So it's much better to actually fail early, let the client retry, and get fresh requests. So with application load balancer, we don't have surge queues, so we have a rejection count. So you can actually see the number of requests that were rejected by the load balancer because we didn't have any way to send them. So if you see this metric, go and scale up your backends. That's what you need to do. Add more capacity, or add more threads on your backends, or add more connection limits, or whatever you need to do in Apache. And then on the target group, so we've got the target group metrics. So those are the metrics we provide, and there are a few others as well at the load balancer level. And then we have these ones at the target group level. So you get great visibility into 200s, 300s, 400s, unhealthy, healthy host count, as well as the target response time, actually latency coming back from the target. And then about 2 weeks ago, we actually launched CloudWatch percentiles. And so we spoke about min, max, and average, and that's what you've had previously. Now you could actually go and say, give me the P90. We say P90 internally in Amazon. Give me the 90th percentile, which means I want to know what's the kind of 90% of my customers are seeing that latency or better. And the way that I run all of my teams at Amazon, or just generally at Amazon actually, is we all focus on the 99th percentile. So when we launch a new service, we'll say, what is your P99? And we watch that all the time. So we watch P99. And the thing is, we're saying 99% of customers are seeing that latency or better, right? And once your P99 is like nice and flat, then you say, okay, P99.9 time. And then you say, okay, start watching that. And that's how we drive ourselves and set aggressive targets all the time to get that latency down. So we never, ever look at average, almost never look at an average metric. We're always looking at 99th, 99.9 percentile. And that's, you're already looking at that 1 or 0.1% of customers that are having a bad day. All right? So we launched this last week, I think it was, and then you can see that's what the graph would look like. So the green line is your P99, P99, the yellow one is your P90, and then the other one's your P50. And P50 is a little different from average, but you'll get that view. So great visibility into the performance of your application. And then, so that's where you want to get a general view with CloudWatch of what are your metrics looking like. If you want to get down to an individual request coming through your load balancer, you want to go and say, why did that request fail? That's where we have access logs. So you can enable access logs, and every single request that comes through your load balancer gets logged to an access log and delivered to S3 either every 5 minutes or every 60 minutes. You can go and set that up. Right? You can decide what interval you want. It includes a lot of stuff: request time, client IP, latencies, request path, server, responses, ciphers, and protocols. So we actually tell you what cipher and protocol that client negotiated with. So if we think about our ciphers, if you want to go turn off a cipher but you want to know who you're going to impact, you can actually turn on access logs and go and have a look, decide whether you should really disable SSL v3. Do you have any customers out there that would not be able to use that? This is brand new, again, last week. Request tracing. That sounds pretty cool. What this does is it inserts a unique identifier for every single request going through the ALB. So you send a new request to the ALB, we'll actually add a unique identifier to the Amazon Trace ID header. And if that request goes through another ELB, we'll actually append a new identifier. So it gets appended. And this, obviously, if you guys saw the release of Amazon X-Ray today, this is feeding information to Amazon X-Ray. So if you go and log this information in your application or forward it for the X-Ray APIs, now you're going to get request tracing all the way through from when it very first hits an ELB coming from the internet all the way through your application. And you can get down into very, very, very detailed analytics with this functionality. So we're pretty excited about that. So we've spoken about quite a bit of stuff. And I guess one of the big questions we haven't covered yet is, when should I use application load balancer? So, I mean, it sounds pretty cool. So when should we use it? When shouldn't we use it? So if we come back to this picture, keep in mind that application load balancer only supports HTTP and HTTPS. So obviously, if you have a TCP load balancer or an SSL load balancer, you'd want to stay on the classic load balancer and continue to use that. For all other load balancer use cases, we rarely recommend trying application load balancer. As I said, for the vast majority of customers, we've seen improved performance with it. You can set it up in a very simple way. We've spoken about a lot of complexity today. Just a single default. The console makes it really easy, by the way. It takes you through in like 3 clicks to set it up, register your instances, and get started very quickly. So with that, it's been great talking to you. I do hope it's been useful. I hope we've shared some good facts. And thanks for coming.